This is Daniel Coosbury, and I'm going to show you how to do a two-sided hypothesis test for the population mean mu when you don't know what sigma is. So we're in a population, we're in a context where we have a population, and we want to estimate what mu is, but we don't know what it is, and so that's the whole point of what we're doing is we're trying to find out what mu is. And we also don't know what the population standard deviation is. So we don't know the mean or the standard deviation, which is different from when we do know what sigma is. So there's a method that exists for when you know what sigma is. It involves using the standard normal distribution. Here we're going to need a different distribution entirely because we don't have sigma. So we start off by taking a random sample, and you can compute things from that sample like x bar. And since you don't have sigma, we're going to use an estimate for sigma as well. We're going to use the sample standard deviation to kind of help us. We're going to use it as a stand-in for sigma, which is going to require us to not use the standard normal distribution anymore, but to use the t-distribution instead. So I'll show you that as I work through this example, how this context changes how you do the hypothesis test, but we'll get through it. By and large, the hypothesis test method works the same until you get to the probability distribution part because the context changed. So I got a question about penguins. Suppose that the mean weight of king penguins found in an Antarctic colony last year was 15.4 kilograms. In a sample of 35 penguins, the same time this year in the same colony, the mean penguin weight is 14.6. Assume the sample standard deviation is 2.5. At a 0.05 significance level, can we reject the null hypothesis that the mean penguin weight does not differ from last year? So we're going to do a two-sided hypothesis test here, primarily because we see this sort of hypothesis. The mean weight does not differ from last year. So what distinguishes a one-tailed test from a two-tailed test is a one-tailed test, you're going to see words like as something greater than or less than it was last year. You're looking just on one side of your mean, but when you see words like did something change or is something different, you really want to see is it greater or less than. So one-tailed would be greater or it would just be less, but two-tailed would be greater or less, which is what will shape our hypotheses. So our null hypothesis has got to be mu is equal to something. Our alternative hypothesis has got to be mu is, this in this case is going to be not equal to, because we're doing a does not differ, but I'll show you what that is. Our only candidate for mu under the null hypothesis is, well, we want to see if it was different than last year. Last year, this is the population mean, so we're going to see if it's still the population mean. So we're going to use the 15.4 as our mu under the null hypothesis. It's really the only candidate here because that's the sample size, that's the sample mean. That wouldn't work. You can't use the sample mean here. That's the sample standard deviation, and that's alpha. So really, this is what it was last year. So the null hypothesis is their mean weight didn't change, and so this number's also got to go here. The alternative hypothesis is going to be their mean weight did change, and by change or it's different, we mean it's not equal to that anymore. So we don't mean less than, we don't mean greater than. We mean it's not equal to that anymore. So this is changed. Our significance level is given to us in the problem. This is 0.05, so this is the probability that we reject the null hypothesis and we're wrong. Yeah, so we want a 5% chance of being wrong if we reject H naught. Okay, so now we're in the, we know we're estimating for mu, and we don't know what sigma is, which is going to affect our test statistics. So when you change this context, the probability changes. When you have to use S instead of S, you're now going to be in the t-distribution, and this is going to be your test statistic. So t, which is equal to x bar minus mu over S divided by the square root of n, follows a t-distribution with n minus 1 degrees of freedom. So that's what this thing is. So we're going to use the test statistic t when we do probability, when we do the critical region method, or we use the p-value method. So to find t, take x bar, which we know, take mu naught, which is the value of mu under the null hypothesis. So H naught mu was 15.4. So that's mu naught. That's what that number is. X bar was 14.6, S was 2.5, and N was 35. So that's what you're going to compute, and this follows a t-distribution with n minus 1 degrees of freedom. So this is going to be the t-distribution with 34 degrees of freedom. Okay, so we can find t. Just do the subtraction, divide by 2.5 over square root of 35, and you get this number. It's approximately negative 1.89, and this is under the t-distribution with 34 degrees of freedom. So now when we move on to the critical region method or the p-value method, all the calculations we do are going to be with the t-distribution using 34 degrees of freedom. So let's start with the critical region method. We want to answer the question, if mu is really 15.4, meaning the weight didn't change since last year, if this is really true, is it unusual if our test statistic is at least as extreme as negative 1.89? And in the two-sided context, by extreme, we mean at least as small or large as negative 1.89. In other words, we want to see what's the chance we get something that is like way over here, like less than 1.89, but also what's the chance we get something over here, which is bigger than 1.89. So we're checking both tails, which because we have that not equal to sign, which is what makes this a two-tailed test. So in this case, the critical region, we're going to mark off the tails that represent the extreme 5% of the distribution. So we want to get the extreme 5% of the distribution. And if t falls in that extreme 5%, then we're going to call it rare. And if t doesn't fall in that extreme 5%, we're going to say it's not rare, and then maybe this mean actually works. But if t does fall in that extreme 5%, we're going to say t is unusual, and this is probably not true. So let's just imagine what it looks like on our distribution. So our extreme 5%, really what that means is we're going to have two tails, and together their area has to equal 0.5. So total, these two areas need to be 0.5. We'll make that a red region. And if both of the areas together are 0.05, and if they're symmetric, that means this area is equal to 0.025. And this area is also equal to 0.025. So they're the same size, and they have a total of 0.05%. So that means this middle part is the middle 95%. So if t falls in this red region over here, we're going to say it's rare. Or if the opposite of t falls in this region, we're going to call it rare. But if t doesn't, we will say it's not rare, and that'll help us draw our conclusion. So now with the t distribution, we want to find out what this number on the number line is that marks off the lower 0.025 and the upper 0.025. So we want to find this number, and this number is called the critical value, and we usually label it like this. So t.025, that's the area above it. It's called the critical value. And just to clarify some terms, the critical region is both of these red regions combined. So they think of these two tails as one region. This is the critical region. That probably wasn't helpful. It's that area. So those two things are the critical region. So we want to find this value on the number line. I think it's a little bit bigger than 2. I did this problem earlier, but it's probably a little bit bigger than 2. Its buddy over here is a little bit smaller than -2. Make that black. And to find this, we're going to use a method similar to using inverse norm. So when we used to do this with the normal distribution on the number line, we used inverse norm. Here we've got to use inverse t. And inverse t takes in two things. You got to tell inverse t the area to the left, and you got to tell it the degrees of freedom, which in our case, the degrees of freedom are 34. The area to the left, well, it depends on which one you want to find. They're negatives of each other. They're opposites of each other. So if you want to find the negative one, just put in 0.025. If you want to find the positive one, put in the opposite of 0.025. I think it's easier to just put in 0.025 and find the negative one. So we're going to do that in our calculator. So inverse t is under second vars, where our inverse norm is. So there's inverse norm. Go down a little bit further. There's inverse t. And my area to the left is 0.025. My degrees of freedom is 34. And I'm going to hit paste, hit enter again, and wait a second, there it is, negative 2.03. That's what it looks like right now, negative 2.03. So this value is negative 2.03. This value is positive 2.03. So if you did it the other way, if you put in 0.975, you'd get positive 2.03. So these black bars that mark off the critical region are these two numbers right here. And so if the test statistic is smaller than this number, it's in the red region. If it's bigger than this number, it's in the red region. And you can see that t is neither in the little tail, the left tail or the right tail. T ends up falling right here, which is in the middle 95%. Okay, so it's not in the critical region. It's right here in this middle section. So why does that matter? Well, the critical region marked off the extreme values, the rare values, the unusual values, and because t's not in there, we're going to say t's not unusual. So is it unusual if our test statistic is at least as extreme as that? We're going to say no, it's not. So let's draw our conclusion. We've marked off the critical region such that any t-value that falls within the region has a 5% chance of occurring or less. Since t does not fall within the critical region, its probability of occurring is greater than 0.05. So we'll conclude it's not unusual to get this statistic if the mean didn't change. If the mean is still 15.4, it's not unusual. And since it's not unusual, we're going to fail to reject H0 because t is not unusual. So if you're looking for a hard and fast rule with the critical region method to draw conclusions, it's this. Since t did not fall in the critical region, you saw that picture, then we're going to fail to reject H0. So that's just always true. So if t is in the region, you reject H0. If t is not in the region, let me show you the picture again. T is not in the region. The region of these red tails, t is right here. If t is not in the region, you don't reject H0. You fail to reject it. So our conclusion is going to be we don't have sufficient evidence to reject H0 and conclude the mean penguin weight is significantly different. That should say significantly different from 15.4 kilograms. That should say kilograms. That is, we can't conclude the mean penguin weight has changed since last year. So this is the nice sentence is we don't have evidence to say the mean has changed. We're not going to say the mean is still 15.4, but the data doesn't suggest it's changed significantly. So we can't reject the null hypothesis. Let's do the p-value method. The p-value method for a two-tailed test is similar in that we're going to look at two tails, and we're still asking the question, if mu is 15.4, if the null hypothesis is true, is it unusual if our test statistic is at least as small or large as negative 1.8? So to do this, let's start by putting the test statistic on the graph. So there's that, negative 1.94. And since we're doing a two-tailed test, this extreme means like at least as small or at least as large as the opposite value. Let's put the opposite value on here too. So these are going to make our two tails. So negative 1.89 and positive 1.89. So if your test statistic happened to be positive, you would put the negative one on there too. Just put both, put the opposites. So our question then is, what's the probability of getting something at least as far away from zero as these two things, at least as extreme as these two things? In other words, our p-value is the probability that t is at least as small as negative 1.89 plus the probability that t is at least as large as positive 1.89. That's what our p-value is. Another way to say that is our p-value is going to be these light green, oops, messed up, these light green regions. So this is what our p-value is. The area of those two things. Now notice this is different than the critical region. The critical region, first off, started a little after 2, and it marked off that 5%, so the cutoff for the critical region was like that. We're getting a little bit more than the critical region. So the area of those two blue triangles was 0.05 total. We want to find the area of the two green triangles, which we know is going to be bigger than 0.05. That shouldn't be surprising. But to do this, we're going to use a function you may not have used before called TCDF. And TCDF takes in 3 things. Before I show you those 3 things, can we agree that the area of these two things should be exactly the same? It's symmetric. Their cutoffs are opposites of each other. So if I find one green thing, have I not found the area of the other green thing? So let's just find one thing. Let's find the area of the left one. T is less than or equal to negative 1.89. And then once we get it, let's just double it. Let's multiply it by times 2, and that'll be our answer. Okay, so we're going to use TCDF, and the way TCDF works is it takes, it's like normal CDF. It starts out with a left side and a right side, or a lower and an upper. And then it takes your degrees of freedom as the special thing, kind of like the mean and the standard deviation, except it doesn't have that. It just has the degrees of freedom. So if I'm looking at the left side, I know the left side goes all the way out to negative infinity. So my left endpoint is going to be some large negative number, negative 99999. My right endpoint is going to be this negative 1.89. So I'm going to go from negative 99999 to negative 1.89, and that'll give me the area of the green thing. I'll double it to get my answer. The degrees of freedom are 34, and so I put those 3 numbers in my calculator with TCDF, and I should get exactly what I need. So TCDF is under second bars, so there's normal CDF. Here's TCDF. And we're going from negative 99999. That negative 1E999 works too. The upper bound is going to be negative 1.89. So that's that number. So see, I've marked off that green region. Degrees of freedom are 34. And that'll give me the area of the left region. Now don't stop here, because remember, that's just the area of the left region. To get the area of the right region, let's take our answer and multiply it times 2. So the area of both regions put together is 0.0673. So this area, this p-value is equal to 0.0673. So the p-value is equal to those 2 green regions put together. In other words, the area of those two regions put together is equal to 0.0673. So that's the chance we get something at least as extreme as negative 1.89. So something at least as far this way or at least as far that way. So that's our p-value. So we found the p-value is equal to the probability that t is at least as small as negative 1.89 plus the probability t is at least as big as 1.89, which was 0.0673, which is greater than alpha. Okay, so we wanted something to be kind of in the 5%, that extreme 5%. This is not in the extreme 5%. This has a 6.0673 chance of happening, a 6.73. So think of this as 6.73%. Think of this as 5%. So this has a 6.73% chance of happening. In other words, if the mean didn't change, if H naught is true, then the probability that we take a sample with a mean at least as extreme as 14.6 is this number, which is not unusual enough. This is not unusual. Because we decided at the very beginning of the problem that 5% was going to be unusual. This is 6.73%, so it's not unusual. So if we fail to reject H naught, we only have a 6.73% chance of being wrong, and that's too big. So let's yeah, that doesn't work here. We're going to fail to reject H naught because this is not unusual enough. So how about that? All right, just copied and pasted something. What I'm trying to say is if we did reject H naught, we have a 6.73% chance of being wrong, and that's just too high. So we're not going to reject it. We're going to fail to reject H naught because that this value, the test statistic, was not extreme enough. It's not. There's a 6.73 chance of getting it. And that's not bad. That's not rare. It's not unusual. Not unusual. Not when alpha is 0.05. So I have the same conclusion as on the critical value method. We do not have sufficient evidence to reject H naught and conclude that the mean penguin weight is significantly different from 15.4. That is, we can't conclude that the mean penguin weight has changed since last year.